Welcome to this M2D2 meeting. Our speaker today is Emmanuel Bengio, and he is a machine learning scientist at Valence Lab, powered by Fusion Pharmaceutical. He's working at the intersection of GFlowNet and drug discovery. And during his PhD at McGill and Miller, he was focused on understanding engineerization in deep reinforcement learning. Today, he'll be talking about his recent research on improving GFlowNet and the application for molecular discovery. Thank you so much, Emmanuel, for accepting to present your work to the community today, and looking forward to it.
Yeah, thanks. I'm very happy to be here. Lots of cool stuff to talk about. Mostly I'll be telling you about either papers that will be at ICML, either as conference papers or workshop paper. Actually, the main bulk of the talk is about this one workshop paper that's pretty cool and recent work. And yeah, feel free to ask questions, interrupt me whenever, raise your hand, or ask questions in the chat. Very happy to answer them. I like my talks a bit interactive. So yeah, I'll first start with a quick recap on GFlowNet. If you're not familiar with it, I think there's been a GFlowNet talk at M2D2, but maybe you weren't there. And then I'll talk about this recent workshop paper where we kind of took this goal conditioning approach for molecular generation. I'll also briefly talk about a collaboration I had about kind of just improving GFlowNet training. And then in the second half of the talk, I'll talk about some work in progress that I'm excited about. One is just about like how to train better, larger GFlowNets. And the other is more investigative, kind of trying to understand what's going on in GFlowNets, what kind of makes them tick and work well for us. Yeah. So I have this slide that I've actually stopped updating because there's no more room, but there are so many GFlowNet papers. It's really exciting to see. If you're not familiar with GFlowNet and my talk isn't enough, there's a bunch of tutorials and material online that I think are good introductions about GFlowNets. And yeah, feel free to check them out. So what's a GFlowNet? There's like these two one-liners that I've developed over time. One is like the more energy-based perspective, and the other is more reinforcement learning perspective. And so the energy-based model perspective is that the GFlowNet framework allows you to train energy-based models. And they're exact in the sense that if you have infinite parameters and infinite time, you train an exact model. And they were cool models in particular because they're O1. I mean, I'm exaggerating here in some sense, but there's no MCMC, there's no diffusion. So you do kind of one episode of generation, you have your object, no burn-in necessary. And in particular, we've developed them for compositional discrete objects. There's been extension to continuous GFlowNets that work okay, but we're still kind of figuring them out. But for discrete object, we've had quite successful applications. And then they work by kind of enforcing this energy preservation, or what we call flow in the framework, in this network of intermediary states, right? So while you're constructing an object, you have states that represent the partially constructed object. And by making sure that you account for all the possible intermediary objects for an object, you kind of end up with the right sampling distribution. The RL perspective, slightly different wording, but it really means the same thing. The GFlowNet framework allows you to find optimal policies in the sense that they maximize reward, but they're entropy regularized. But the entropy here is not the entropy of the policy, instead is the entropy of the terminal distribution, right? So if you have a finite pointer DAG MDP, so one initial state, finite MDP, and it's a DAG, so you can only go one way. You can train these models using off-policy objectives. We actually found a bunch of objectives that work quite well for this, and they're all off-policy. Of course, assuming you visit every state once. And this is pretty cool from an RL perspective because you don't actually have to estimate this terminal distribution explicitly. It's done implicitly in the weights, the model that you're learning, as long as you are truly having this pointed DAG, and you have some kind of access to the model where kind of the minimal requirement is that you could at least parameterize a distribution over parents. So not just the forward policy in some sense, but also a backwards policy. And how do we train these things? So just kind of the recap of the idea, right? I mentioned flow preservation, energy preservation. You can think of an MDP, right, of the generating process as this diagram where there's some flow that goes to the edges. And what you want is the flow to be preserved, right? So there's just as much flow in these terminal nodes as there is reward or energy for that state. And you basically want to find a model that predicts these edge flows in such a way that all the flow that goes into a node is the flow that comes out of a node. And the most popular parameterization right now is based on the trajectory balance paper. And it's basically about splitting the flow with these forward and backward policies. So the way I think about it is that you learn this partition function Z, which represents the total flow. And what you want is to match for any trajectory kind of the fraction dictated by the forward policy of that flow. Right? So you have a particular trajectory, the policy will give you a distribution over trajectories and forward paths. And so you'll get a fraction of the flow kind of allocated to that particular trajectory. And you want that to match the backwards, right? The backward path. So you want that the flow that kind of comes out of the reward and is going backwards to be equivalent. And a neat thing that I'll talk about later is that you can parameterize this PB, of course, but you can also choose it in some sense. It can be some constants like the uniform backward policy. It can be some heuristic. And this will kind of control where flow is allocated, not just in the backward way, but in the forward way, because they do have to match, of course. Right. So for example, in this node here, S11, you see there's like 2 parents. And so by controlling going backwards where you want the flow to be, by controlling the legits of this backward policy, you're also controlling which paths towards S11 get more probability. And so training this kind of model induces this kind of energy-based distribution where the probability of sampling some given X in terminal state is proportional to the reward. And why is this good? Because GFlowNets try to find all the modes, right? They don't care how you get there. If you have some reward and you're sampling from it, it's going to be proportional to it. And like the analogy we like to give is in RL, typically you kind of only care about the max, right? You care about the policy that maximizes the reward, but you don't really care how you get there in some sense, as long as the reward encodes it properly. Whereas GFlowNet does something entirely different in some sense. It says, find all the modes of the distribution. Why is diversity good? There's 2 reasons that we think basically are good. One is more like ML related. Of course, if you have a model like a deep neural network that does systemic generalization, then with only, let's say, these blue data modes, the model should be able to predict that it has to sample from the 4th red mode. And because models like GFlowNets are typically trained online, saying that as the model learns, it decides what it's going to sample, then you get this good self-induced data distribution, which we think makes GFlowNets generalize very well. And the other reason diversity is good, I think I shouldn't have to convince you here in this crowd, but the real world is full of unknown unknowns. And so when using proxies, for example, in synthetic chemistry, we want to cast a wide net, because if our model of binding energy or whatnot is wrong in 3 out of the 4 modes, then you're hoping to get all of them in some sense. And so having a very wide distribution is quite important. Let me stop here for a second, see if there are questions or comments, or people don't understand anything. All right. Yes.
I think so far so good.
Okay. Cool. So I'll talk very briefly about this paper because it's an old paper by now, even though it's going to appear at ICML. It's been out for a while, and basically in this paper we show you can train GFlowNets to do multi-objectives in a fairly standard, straightforward way by doing scalarizations. Right? What does that mean? If you have multiple rewards, multiple objectives, you combine these objectives, and here, for example, in the linear scalarization, you have this preference vector. You simply do a convex combination of them, and you end up with a scalar reward. By learning a conditional model that's conditioned on this omega vector, you end up learning a family of distributions. And this family of distribution, by sampling from it in a smart way, or even just kind of uniformly, just generates the Pareto front by virtue of kind of trying all the possibilities of combinations of rewards. And what we show also experimentally is that by doing this, you combine the diversity in terms of like generating the Pareto front, but also within a location on the Pareto front, because GFlowNets are pretty diverse models by design, you also get diversity there. That's pretty useful. Maybe to kind of concretize this intuition, just going to show the result on the molecular task. Right, so here we have 4 objectives: binding energy, QED, detect accessibility, some weight constraints. And what you're seeing on the diagonal here in orange is kind of preference in, reward out, right? So if the preference is very close to 1, you'll see that the model tries to generate stuff that has some high reward here on SEH, which is the binding reward. And here you see all the pairwise kind of Pareto fronts and the distributions that are induced. You see that the model kind of recovers a nice distribution and finds all these Pareto high reward points. And we started actually using these models internally at Recursion. It works relatively well, but they have multiple problems that have been discussed before in the literature. But in particular, one is that when you scalarize multi-objective problems, your solution is going to be quite dependent on the shape of the front. And what do I mean by that? Let's say you have this problem and you're scalarizing it, and you change this parameter alpha to kind of generate different solutions. If your Pareto front is convex, kind of fine, right? You'll end up with different solutions because the alpha kind of induce a nice different trade-off. On the other hand, if you have a weirder shape like concave, not even that weird, you'll end up having these weird solutions where the points in the Pareto front are not stable. And this induces all sorts of problems, which kind of favorize models, even GFlowNets, to kind of sample from the edges of the shape. And that's, of course, not good because actually we're typically interested in these points in the middle. And so, one way to try to understand why this happens, you can think of it even in terms of SGD, right? If you have something concave, if you take a tiny step in either direction, in this direction, for instance, the gradient towards this edge, this corner, will be larger than the gradient the other way, and so you kind of tend to slide off, which doesn't happen, of course, in the convex cave, where you kind of tend to converge to a point. I think this is very well known in optimization, so if you're familiar with that, shouldn't surprise anyone. And so to kind of address that, we took inspiration from reinforcement learning and kind of developed these goal conditioned GFlowNets. And I have to say, this is mostly all the work of Julien Roy, who was my intern this winter at Recursion. And so what's the setup, right? Remember these pairwise objective figures. What we're going to do is kind of define goal directions, right? So vectors kind of pointing somewhere in the quadrant. And we're going to say, if the cosine similarity between the reward point you get and the direction is close enough, right, bigger than some threshold, then you give the usual reward. If not, you give 0, right? So you're going to mask out all this space for a particular goal. If you do that, for one fixed goal, you end up training a model that will just sample from that, right? Zero reward is going to avoid places where there's no reward. But of course, you want to sample from everywhere. So what do? Kind of sample uniformly from all the possible goal directions. In 2D is going to look like that, right? But as you go up, you can think of wanting to sample uniformly in the hypersphere or something like that. And of course, condition the model on the direction of the goal so that it knows where to actually sample in an episode. And you end up with a model that effectively is able to sample from the right region in objective space. And what we find is that it's actually quite nice because the distribution and the goals that you choose will kind of induce the model to have a nice distribution. It'll force the model to basically it'll force the model to explore everywhere you ask it. And so, in a normal convex kind of setting, there's not much difference. What you're seeing, the coloring here is kind of the angle of the goal, right? So if the goal, let's say, was to go there in that direction, so to go to the bottom, to the top left corner, then you're going to color the point blue, and there's like this gradient from blue to green going through red for the opposite corner. And you can see that even though the results are the same, even then you kind of get more controllability. Right? There's a clearer demarcation when you ask the model to find something, it will actually go where you ask it to, which is not the case when you do what we call preference conditioning, which was basically just linear or log linear scalarization. Another advantage of the goal condition case is that kind of force the model to explore everywhere, even if it's a terrible region and there's no reward there. Why might that be good? Typically, you wouldn't want to actually, send these molecules to the lab, but you want to show these molecules to the model. I think there's a few results showing this. You do want to feed in negative data to your model to show it what not to do in some sense. Or if you have a reward model, you want to show it low reward examples so that it knows how to contrast things that work from things that don't work and understand what are the factors of variation. So anyways, back to the Pareto front shapes. These are artificial, of course, but again, you see the top row is the original multi-objective model. Bottom row is the goal condition model. The goal condition one is way more robust to all kinds of things. And in particular, when there's like extremely great shapes, you actually can break optimization in some sense for the preference condition model. So you might ask, like, why did we do this? First of all, I think it's a really cool figure, but also in multi-objective with lots of objectives, not just two objectives, the Pareto front shapes tend to be really weird. And so it feels very important to actually end up having these methods that are robust to non-convex Pareto fronts. So quick note on how we evaluated that work, just because here we were particularly concerned with the shape and the kind of matching everywhere and finding solutions everywhere. We use the typical inverse generational distance, which basically just computes how far you are from the ideal solution, which is something you want to minimize. And then we also computed what we call the clusters entropy or Pareto clusters entropy, which again, you have your ideal solutions and you look at the closest point to each ideal solution, and then just count how many points match each ideal point and look at the entropy of that histogram. Right? And ideally, you want something with pretty high entropy when you query your method uniformly, and a high entropy would just suggest that your method is kind of sampling everywhere. Right? Why don't we only care about the hypervolume? Again, this goes back to my slide on unknown unknowns. We don't just want to show, let's say, the chemists these very extremal points. because there is uncertainty about the reward. There's uncertainty about the predictions that your model might be making, or even, something like log p, right? You're interested in a range, not just the best one. And so it felt important for us to have metrics that reflect that. Thus the choices of metrics. And so using these metrics, is there a particularity of GFNs that allow the goal-directed optimization to work that well? I mean, you could do that in some sense with anything, right? With RL or even diffusion models. I think there's a good interplay between the natural tendency of GFlowNets to explore and to be generous and to kind of cover the entire state space. One typical pitfall, for example, of RL methods is they kind of collapse to a few examples in distributional sense. And it might make them not too robust to conditioning, right? So even if you have kind of high entropy from the RL, each goal conditioning would kind of collapse to a single point. And that could fool you into a false sense of security. And so, like, could this be achieved? Yes, of course. But I do think that this plays well with GFlowNets' natural kind of diversity-inducing behaviors. And I guess there are genetic algorithms actually that do something similar. So they purposefully in the forgetting the word, but in the cloning phase and the killing phase, kind of heuristically choose clusters that are far away from each other in both objective space and, let's say you're doing molecules, studying local space or some other distance metric. So this is also something that is kind of done implicitly by other genetic methods. All right, so of course we care about scaling because we have complex problems with lots of states and lots of objectives. And so one thing that happens, of course, with sampling and sampling uniformly is that as you increase the number of dimensions, of course, increase of dimensionality, less and less of the space is feasible. And by that, I mean the objective space. As you increase the number of properties of a thing, there's less things, there's less objects that have exactly those properties. And so this is reflected here if you look at the right. Even if as we increase the number of objectives, the kind of Pareto optimization still happens. The entropy is high, so we have a nice cover. But the goal reaching accuracy gets really low. And this is both because, I mean, we've kind of debugged it. This is both because, well, it's harder to satisfy more objectives, but also there's more infeasibility. There's points in the state space that literally have no objects that satisfy. And so as a solution to that, we thought, well, instead of kind of always uniformly sampling from everywhere, maybe we should just narrow down the distribution of goals that we ask of the model. And so what we did for that paper, but I'm sure we could do much better, is basically just keep track in a tabular model of all the directions that have been actually populated, right? So when the model samples something, if it's in a particular region, just count it. And then decrease the likelihood of directions where we never find anything. And, right now, again, this is done with a big table, which is not great because as the number of dimensions increase, you need more. If you kind of discretize your model, your objective space in the grid, you need more numbers for that grid. But you could use something like a GFlowNet actually to do this. And Julien kind of started trying it, but ran out of time and it didn't work too well, so kind of dropped it. But you could use any model and turn it into some kind of hierarchical GFlowNet or hierarchical reinforcement learning kind of setup. And of course, if you do that, here we kind of turn on this focus model at a quarter of the training. And you see that for 3 objectives, it kind of immediately starts being able to find goals all the time. And for the 4 objective, it's not perfect, of course, because 4 objectives harder, but it gets better. And of course, what's nice is doing that not just helps with the goal reaching accuracy, which is kind of a side effect of the model, but really with the performance of the model in terms of Pareto optimality. Yeah. And I guess some other tricks that are pretty fundamental, but I think have been used generally by the GFlowNet community is replay buffers. Very important. Not so much that they give you better performance in some sense, but they stabilize learning by simply offering a smoother distribution when you're doing gradient descent. And that can be useful in preventing models to diverge and all kinds of things. For this particular work, we did some hindsight relabeling. So if you're not familiar with the hindsight experience replay paper, the idea is pretty simple. If you kind of reach, you're queried to reach a goal, right? But you reach somewhere else. Well, you're gonna add that experience, that pretend, oh, I actually wanted to go there experience to the replay buffer as well, and train on that. So even if the model kind of fails reaching where you wanted it to go, it's at least learning something about where it went. And then, of course, smoothing is also very important in general in GFlowNets and reinforcement learning. Reward shaping is pretty important. And so here, instead of kind of doing a very dry cutoff, if the angle of our goal is greater than where the reward was, we kind of do this smooth going to 0. And yeah, my number is bigger than yours. This works better than the linear scalarization. And in particular, if you'll recall the plot that I showed you earlier with the conditioning in orange, right? Conditioning on the y-axis and reward on the x-axis. This was the linear scalarization method, which still worked pretty well. If the conditioning was high enough, would give a result that's close to what you want. But with goal conditioning, there's way more controllability, and that's very satisfying from a practical perspective when you have a back and forth with, let's say, a chemist, and you're like, well, I actually want a bit more of that region, that log p. Then you can just go back to your model, adjust the angle, and sample them. And again, the kind of angle colors here showing that the model is really able to respect what you ask of it. That's very useful, on top of finding a better Pareto fund, of course. So I'm going to stop here, again, checking for questions and comments.
I have one question. So one thing you showed previously is how the satisfying the optimization criteria decrease as you have add more objectives, and you are playing only with 4 objectives. In drug discovery, for a fact that we have a lot more objectives. So just wondering if you have tried with more objectives and if uh, the method you have introduced to improve the result here help when you have even more of the objective and yeah.
The highest we've been in is 8. I guess one thing we haven't tried, I mean, and it does help even with 8. I guess one thing we haven't tried is the kind of massively multitask model where like each task is a different protein. I don't know that I would use exactly that framework, although it could be cool to try just to see what happens. But yeah, we haven't tried that.
And when you are training with the different objective, I guess, is it the same policy for all the objectives? Like you just colorize and use the same policy? Oh, okay.
Yeah, you just feed in. I actually don't have it, but you feed in the direction as the conditioning input to the model at every step of the generation, and it knows how to use that to change the distribution and the reactions.
Okay, I see. Thank you. There's a question by Lena in the chat.
Yeah. Is there a generalizability in learning the directions of the goal? How does learning the reward in one goal direction give information about the other direction? Yeah, that's a good question. This is an interesting point, actually. Or actually, this is a good figure. So, like, one thing that works well, unfortunately, is discretizing all the possible directions, not always feeding the same directions to the model. But that's kind of dangerous because then you reduce the span of what the model can do. So you can feed in scalars and let's say sample from a uniform distribution. That works well, but not as well as discretization. And it's just because it's a harder model, it's a harder function to learn. Right? You're learning over a larger family of distributions, and that makes it harder. In terms of like generalization from one goal to another, it's not something we've measured precisely, but I think it must happen in the sense that the hindsight replay helps, right? Another way to think about it is that this is it's probability model. So if you increase the probability somewhere or decrease the probability somewhere, inversely it kind of balances this out. So there's probably some interplays there. Hopefully this answers the question, Lena.
I have a question.
Yeah, go ahead.
Do you think that this approach of goal conditioning, which seems to work well in your application, could be applied to design better exploration policies, whether in regular RL or for the policy that we want to train for GFlowNets?
I'm tempted to say, of course, and it's just because of this little result here, where we forced the model to go in that direction, right? So it's basically 0, 1, and it still managed to find a few points, even though like there's obviously nothing there. And I would call that exploration, right? We kind of force it to visit states, right? This is objective space, but really we're seeing results in the state space of points that it otherwise would have totally ignored.
Right, but how about generalizing this to the problem of finding good modes, in the trajectory space?
Yeah, one thing that surprised me with this entire paper is that you can be really severe with the model and give it 0 reward in almost all of its state space, except one tiny slice of it. And as long as you kind of visit the slice intelligently, it seems to be able to really respond to that well, or only sample from that slice. And I think this, in fact, we've observed something cool, which is, don't believe I have it in those slides, but let's say that this direction was totally infeasible. Then you revert to a reward 0 everywhere situation. And what GFlowNet does for that? Well, spread probability mass everywhere. So it's like a natural exploration mechanism when the model is unable to satisfy the goal.
That's cool. Thank you.
Cool. There's no other questions. I'm going to talk just one slide on this paper. So this is work almost entirely by Max Shen, but I've had really nice discussions with him. And these are all Genentech / appreciation design folks. And so there's a lot of results in this paper, lots of experiments, but there's really a few things that stand out. Of course, is that I think, we've known, I think early on in the GFlowNet community, we would all use like uniform backward policies. Pretty quickly, we realized that if we actually parameterize them, makes the optimization problem harder. but it wasn't clear like what should happen to PB. And one thing that's interesting in this paper is that Max was like, well, what if we just use a heuristic PB? So in this paper, the PB is entirely kind of hard-coded in some sense. It's a small algorithm that looks at the data set and outputs a number. And what it outputs is a preference over states, over intermediate states, which have subgraphs that are in lots of high reward states. Right. So for example, here you have this molecule, and there's multiple ways of generating that molecule. But one of them contains the subgraph, which is also in all these target binding molecules. And so by simply saying, well, PB should be higher here than it is here, you're influencing also PF to prefer these paths. And this kind of improves performance, makes the model learn faster, and generally is a good thing. And so, this is not something that you might necessarily want to use in practice because here PB is like handcrafted, but it hints at something, which is that, of course, PB is a really useful knob over kind of the inductive biases that you choose for your model. Other results from that paper that are kind of related, again, replay buffers are helpful if you do them the right way. Another result that's kind of orthogonal to all of this is that one of the improvements you can do is by predicting the edge flow in a slightly different way. And what this hints at is just that forcing the model to predict the flow seems to give some boost to generalization, right? So there's something about the flow prediction and the flow function itself that says something about the structure of the problem, which it seems important to give to the model. And again, hammering this in, that like flow allocation, and you can think of it whatever way you want, seems pretty important.
Is the flow prediction happening on a separate head of the same network, which would explain why it would help?
So there's two experiments. One is that, and one is very inefficient, but is predicting the edge flow by literally feeding in the two states as inputs. And that works well in terms of generalization, but of course costs a lot because if you have n children, you need n forward passes just for like to compute PF. And predicting the flow works better than like just predicting the logits in that sense.
Okay.
Yeah, so that was mostly it for papers at ACML. Do want to talk about some work in progress, stuff that I'm excited about, and hopefully will excite you about GFlowNet. So one way to kind of sample better data, better training data for the model, if you have data or even just a replay buffer, just actually sample around it. Right, so this is a figure from Dinghuai's discrete probability modeling paper, but the idea is very similar. It's totally valid in the GFlowNet framework to take, first of all, subtrajectories and train on them, which is very cool. But also we can take different paths, right? So let's say you have this well-known molecule, you can kind of progressively deconstruct it using your backward policy, and then construct an entirely different molecule using the forward policy. You can construct the same molecule using the forward policy. Kind of doing that, you can think of it as a form of local exploration, because instead of kind of starting from scratch, from the empty molecule every time you sample something new, you're actually working around your existing data buffer. But this is not, of course, MCMC in the sense that you're not doing one-step transitions. You're kind of zooming out, allowing for a wider subspace to be reached, and then trying to reach it. And of course, the knob of how far back you go, or the distribution of how far back you go, is this nice spectrum between doing pure MCMC and kind of fully online, start from scratch GFlowNet. And at Recursion, we've used this to do lead optimization, and it has been interesting and appreciated by the chemists. Another thing you can do if you actually have data again, is as I was saying, try different paths, right? So if your model tends to want to generate a molecule using a particular path, but it's giving like very high likelihood to that path, one way to regularize it is saying, I'm going to let you construct that molecule again, but using a different route, right? So what I was saying in the previous paper is you can kind of force the credit assignment to be just in one path. What I'm saying here now is there's a whole spectrum of doing this. You can go uniformly backward, but you can also kind of do a mix between the two. And doing that kind of naturally promotes exploration, I believe, because it forces the model to learn about different intermediate states. And so doing this kind of approach in something that's more like scaffold hopping, forcing the model to have a wider distribution also worked pretty well. Yeah. Just a little pause here, but I don't see any questions. So I want to finish just talk on like some other very more investigative work. This is maybe a bit less molecule related. I'll apologize, but I think it's pretty cool. So first start by the setup and then show the cool result. So here I'm trying to investigate GFlowNets on this minimal graph problem. Right, so you can build up to 7 nodes, up to complete graphs, and each node can be of 1 or 2 colors. Right, so we can enumerate all the possible states. There's about 70,000 of them. And the neat thing about the setup is that you can actually compute P of X given data fairly quickly, which is normally intractable. And what I'm going to do is take this setup and train different models on it and define different rewards. So from hard to easy, all right, one model that has to identify cliques, which is a pretty hard problem. One reward, which is this about counting neighbors. So the model has to, the graph neural network has to learn about edges. One is just counting. So the model can totally ignore edges and just count nodes of every color. And one is just a constant reward, which you think would be easiest, but isn't necessarily. And doing this and kind of training first a model to regress, kind of verify the intuition that there is a ranking between the rewards in terms of training a graph neural network on them. So here I'm doing that and showing, well, there's a gradient in difficulty. And here I'm showing the distributional errors that the model makes when training a GFlowNet on these rewards. And so here on the left is the Jensen-Shannon divergence, and on the right is this kind of absolute log P error. And some interesting tidbits. You'll notice that the constant reward is not trivial. And of course, the problem with the constant reward is that the model has to learn to actually go everywhere, which is not an easy task. Whereas for other rewards, for example, the cliques reward, fairly few graphs have a high reward. And so the model kind of only has to learn in some sense to give high probability to a few places. And so, even though the constant reward is kind of easiest to learn, in some sense, it's comparable to others. And again, as I've mentioned, there's some differences in the kind of shape of the distribution of rewards, and so this might change the ordering. But generally, good news, training a GFlowNet is about as hard as, well, not about as hard, but the difficulty kind of matches. The difficulty of training a reward, trying to predict the reward is about as hard as training the GFlowNet on that reward. And the result that I think is pretty cool is that if you train GFlowNets offline on a data set and even allow it to overfit, it's still giving pretty robust predictions. And particularly the ranking is very well preserved. So here I'm kind of showing a table of numbers, but maybe you can only focus on this graph, which shows the predicted probability on the x-axis and the actual reward on the y-axis. And you'll note that for most of the points, the test points that are in orange, the the probability predictions are pretty good, even though the model, I'll remind you, isn't directly predicting these probabilities. It's predicting the probabilities of each actions in the trajectories, except for these few points that it's hallucinating. In some sense, I'm not worried about these points. And the reason is that typically you wouldn't actually train a GFlowNet like that. You would train a GFlowNet in an online way, in the sense that it's allowed to query new points that it wants to visit and receive feedback from it. And so either in an online or in an active learning setting, it would pretty quickly gather these points and probably learn from them that they're kind of extreme maybe examples or something like that. And adding them to the train set should make the model better in generalizing. And yeah, so kind of to recap my talk, multi-objective GFlowNets, but maybe more generally multi-objective setups can be made better by kind of learning these narrower distribution, but like a family of them. And another kind of good result in the same sense is that the GFlowNet framework is surprisingly robust to having these hard constraints, having these very narrow regions. Multiple papers, I think, now confirming that replay buffers are good, and we should really investigate like what are the right ways to use replay buffers with GFlowNets. Also results that like intermediate paths matter a lot. And again, this is another difference between like the GFlowNet framework and reinforcement learning. This is not something that's typically tackled by reinforcement learning, other than in some various kind of intrinsic motivation aspects, which are not typically very deeply investigated. If you have data, there's lots of things you can do. And again, that's thanks to the fact that GFlowNet objectives are off-policy objectives. Also, cool results about like flow and how predicting the flow seems to be a useful quantity. I think it's interesting to see that this kind of artificial construct that we came up with is a useful quantity for generalization. And of course, this last result that even overfit GFlowNets tend to generalize in an interesting way, especially in terms of rank. So I see a question in the chat. How do I envision the future integration of GFlowNets into the drug design pipeline? I'll start with that question because I'm more. So, I mean, anywhere you design your compounds, you can use it. I think when I started using GFlowNets, the general sense was that it would be really more useful in de-novo because, again, it's something that likes to explore a lot, be really diverse. And so because of that kind of trade-off where, well, if you explore more, you exploit less, I think the sense was that it would be more useful when you want to come up with hits and not necessarily like optimize them. But you know, that was like a year and a half ago. Since then, we've successfully used GFlowNets in lead optimization. And so I think there's no reason to think that they couldn't be everywhere in the drug discovery pipeline. This is totally not my work, but there's people using GFlowNets for entirely different things. For example, because recovering latent structures, recovering causal graphs. These are also extremely useful in drug discovery. And yeah, I'll stop there. But like, there's a bunch of places where we should be really excited by GFlowNets, I think. In terms of ethical consideration, I mean, you know, we're doing drug discovery. There's a bunch of ethical and moral problems that come with that. I don't think GFlowNets in particular are particularly better or worse than other methods. So I want to go deeper in that in the answer. And how can we compare them? Well, I mean, this is basic paper writing where if I don't have baselines, the reviewers will not like me. So of course, there's a bunch of papers coming up every year, especially now that graph neural networks are getting better. Just typical MLE papers, latent representation papers, stable diffusion papers applied to molecules. there's lots of things to compare ourselves to. And I see your hand raised by Joyce.
Hello.
Hi.
Hi, can you hear me?
Yep.
Yeah. Right. So yeah, thank you very much for your presentation and general for the work on GFlowNets. Me and my lab in KAIST in Korea, we work on drug discovery, and me and a colleague of mine are very interested in integrated and trying out GFlowNets in the 3D domain. Would you think that GFlowNets, as they are now, which is basically a compositional graph model, would be able to work for example, in the 3D protein candidate or cryptic pockets or something like that, without any major modifications? Because I think what I've realized from reading the papers is you either rely on the reward, which is a very good proxy, or you jointly train with an energy-based model, or I don't know if that's a correct understanding there.
Well, okay, two things. First, in any search problem, regardless of the algorithm that you're using, your search algorithm is only going to be as good as the reward or the energy you're using. Of course, some kind of intermesh better than others with the reward, but like, I guess it's a fundamental limit of substance. In terms of specifically, protein configuration or cryptic pockets, I think there's a lot of work to be done. We know how to do continuous GFlowNets at let's say theoretical level. The practical level, we still have to figure out the kinks, although I believe several people at Mila are working on this. And the potential really cool thing is that because a lot of these physical systems actually give you an energy function in a very natural way, you can use that energy function kind of as is for a reward if you want something that samples it. Of course, I'm saying that like it's easy. No, it's a lot of, I think, like algorithm design, as I was saying, things like replay buffers and various things, various training tricks are going to be very important. But purely in the theoretical terms, yes, GFlowNets can definitely be applied to these problems.
All right, thank you for your answer. Yeah, I was more thinking about how we could integrate like geometric inductive biases, because yeah, it's only if I try to think of it in an RL frame, that's not really. Of course, there've been some papers, but yeah. Anyway, I will follow up with the work and come back at you. Yeah, thank you very much for the presentation.
Yeah, thank you. Actually, I'll use that question as an excuse to bring up this slide, which is part of my extra slides. You're mentioning like the distances and then the structure, the 2D structure. That's something that you can do as part of the input. Like you want to give information to the model so that it can do predictions or generations in the right way. And I had this slide in my reinforcement learning in the real world talk. And I think, as I've been reading lots of papers now in the field of molecular design and machine learning, people often conflate like their, let's say, practical generation algorithm design with the underlying MDP that they use. Yeah, the structure that they give to their algorithm to design new molecules. And I think it's unfortunate because these two are kind of separate in some sense. One is the algorithm that you're using on the MDP, and the other is the MDP itself. And as far as I know, in reinforcement learning, there's very little either theoretical or practical research that says, here's how you should actually design an MDP to really enable RL, but also, I think, more generally, MDP using algorithms to work well. Right? There's it's known that RL is sensitive to like how actions correlate with each other, the number of them, partial observability, all these things, right? How a state is featurized. I think that's well known in machine learning. Like you want good features for your model. And so I think orthogonally to new algorithms that achieve higher numbers, we should really think about, protein design and molecular design. What are the best ways, or maybe the multiple best ways, depending on what you're trying to do, de novo lead optimization, to kind of phrase the problem of optimization. So anyways, stop my rant here and go back to the conclusion.